critically second year. So today I am gonna explain sequential circuit and system. Welcome to the world of sequential circuits. This presentation dives deep into the fascinating realm of circuits that remember their past, allowing for integrate logic operations beyond the capabilities of their combination counterparts. Prepare to unravel the intricacies of flip-flops, registers, counters, and memory elements as we explore the fundamental concepts and real-world applications that make these circuits essential in our digital world. Combinational versus sequential, understanding the core difference. So, combinational circuits, the output at any given time is determined by the current input values. They don't have memory, so past input changes have no impact on the present output. Think of a simple logic gate like an gate. The output is high only when both inputs are high, regardless of their previous states. Sequential circuits. Sequential circuits, on the other hand, hold informations about their past states. They remember previous inputs and use this stored data to influence their current output. Imagine a light switch with a timer. The light stays on for a certain duration even after you have released the switch. This memory feature allows for integrate logic sequence and complex behaviors. Flip-flops, the building blocks of sequential logic. Acer flip-flop. The Acer flip-flop has two inputs, set and reset. It can be set to a high state by applying a high signal to the S input or reset to a low state by applying a high signal to the R input. D flip. The D flip flop has a single input. The output follows the input on the rising edge of the clock signal, latching the data value. It's a versatile building block used in memory and shift registers designs. JK flip-flop. The JK flip-flop has two inputs, J and K. It combines the functionality of the Acer flip-flop with a toggle option. When both J and K are high, the output toggles between 0 and 1 each clock pulse, making it deal for counter application. Register storing and manipulating data. Data storage. Registers are essentially groups of flip flops, each capable of storing a single bit of data. They form the core of memory systems, holding information for later retrieval and manipulation. Data shifting. Shift registers are designed to move data bits sequentially by applying clock pulse by applying clock pulse. They can shift data values to the left or right, enabling applications like transmission and serial to parallel conversion. Data processing. Registers are essential for performing arithmetic and logic operations. They can hold operand stores intermediate results and manipulate data through a series of sequential steps. Sequential steps. Counters, counting and timing events. Binary counters, asynchronous counters, synchronous counters. Binary counters. Binary counters increment their output by 1 for each clock pulse, cycling through a sequence of binary values. They are commonly used in digital clocks, frequency dividers, and timing circuits. তারপর হচ্ছে asynchronous. In asynchronous counters, each flip-flop is triggered by the previous flip-flop's output, creating a cascading effect. Creating a cascading effect. They are faster but less precious than synchronous counters. Sorry, synchronous counters. What is a synchronous counter? Synchronous counters use a single clock signal to trigger all flip-flops simultaneously, ensuring precise counting operations. They are complex. They are more complex but offer higher accuracy. Memory elements retaining information. Stack RAM. SRM uses transistors to store data, holding it as long as power is supplied, is fast and low latency but consumes more power and has lower storage density. DRAM. Dynamic RAM. Dynamic RAM use capacitors to store data requiring periodic refresh cycles to prevent data loss. It has higher storage density and lower cost but is slower than SRAM. Static RAM. ROM stores data permanently during manufacturing. It's not valuable and retains data even without power. It's used for storing boot programs and other permanent data. Analyzing sequential circuit states and timing diagram. State diagram. State diagram depicts the behavior of sequential circuits showing different states and the transition between them. They use nodes to represent states and directed edge transition labeled with the input condition and output. Timing diagram. Timing diagram visualize the relationship between inputs and outputs and clock signals over time. They show signal waveforms and their relative time, aiding understanding the circuit's dynamic behavior. Real world application from clocks to computers. Digital clocks. Counters from the heart of digital clocks, keeping track of time, incrementing their output with each clock pulse. They are also used in timing circuits to generate specific delays. Computer memory. Memory systems in computers really heavily on flip-flops and registers to store data, program instruction, and operating system files. They are crucial for program equations and data access. Digital controllers. Sequential circuits are employed in digital controllers to manage complex processes. They use state machines to transition between different modes of operation based on input and feedback. Thank you.